we're recording. Yes. So welcome everyone again for this new Graviticulas seminar. Today we have Ariel as the speaker, and as a summary of his career, he got his PhD at University of Santiago de Chile in 2016. He did his first postdoc at the University of Florida in USA. In the period of 2018 and 2019. And currently he's doing his second postdoc at the Institute of Theoretical and Mathematical Physics of the Lomonosov Moscow State University. I hope I said that okay. So please, Ariel, go ahead with your talk, and thank you very much.
Okay. Thanks. I'm glad to be here again. Okay, I will show you an idea that was proposed like 2 or 3 years ago, and it's still we are still working hard on it. Sorry, I will close Facebook because it's
don't worry. And okay. Can you try to put like presentation view, because we don't see the part below of your slides?
I'm sorry. Okay. What about now?
That's perfect. Yes, thank you.
Okay. So yeah, this is an idea for axion dark matter detection that was proposed like 2 or 3 years ago by Pierre Sikidi and I. And yeah, and now in this talk, I want to update how it's going, because we have the first proposal, but we are working hard on it to to see if we can go to the next step, which will be like more an experiment, an experiment. So let's first introduce the axions, which has the axions are very motivated because they can solve the strong CV problem in QCD, and they also arise as ultralight dark matter candidate. So it is expected that for an axion mass of 10 to minus 5, so we can see that they are lighter than neutrinos. Okay, they can fulfill the dark matter of the universe. So yeah, this is for the QCD axion, and on the other hand, we also have axion-like particles motivated by another extensions of the standard model. So we have like okay, and these axion-like particles are not constrained by as the QCD axion is constrained. So we have like a wider window where the axion-like particles can be, I mean, in respect to masses or respect to standard model couplings. So one interesting thing from the experimental point of view is the coupling of the axion into the photon field. It's given by this Lagrangian. So we can see that the axion coupled to 2 photons. That's important for what I am talking is in this talk. Yeah, most of the experiments, there are also experiments which look for interaction between axions and fermions, or another standard model particles, but usually what is more exploited in the literature and in experiments are this coupling to photons. So we have this kind of these are some of these experiments, but I don't want to stay here, I mean, in this section too long, so I will just move forward. So this is the current status in axion searches. So the color regions are the bounds, and this yellow this yellow line is this yellow band is where the QCD axion is. The, 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 um, the other region corresponds to axion-like particles. So one interesting thing is that the axion, indeed, the QCD axion, you can see that it's just explored vaguely. So you can see that there are a few experiments, for instance, this ADMX, that are able to reach the QCD axion, the QCD axion parameter space. Okay, we also have, for instance, this region here, right? But this green, but for these axions, they are not motivated to be the dark matter. So the dark matter window is actually in this part, let's say between 10 to minus 7 to 10 to minus 3 electron volts. Okay, it's controversial. One can say it can be a bit for smaller masses or for higher masses, but it's usually in this range, at least for the QCD axion. So yeah, that's interesting because we need experiments or observations able to prove this parameter space. So okay, I will talk about the idea. The idea is that okay, as the axion couples to 2 photons, so and as the axion has a mass, we can expect that the axion can decay into 2 photons, right? So if we calculate the lifetime of a single axion, this will be the formula of the lifetime, where m is the axion mass and g is the coupling to 2 photons. So for a typical dark matter axion, here I am giving some numbers for a typical dark matter axion. One can find that the decay rate, sorry, the lifetime of an axion is of the order of 10 to 42 years. So that's so big, much more than the age of the universe. So one expects that the axion is very stable, right? Actually, it's the dark matter, so it should be stable. Yeah, so one expects that the axion never decays into 2 photons spontaneously, at least. So of course, if we have a very huge occupation number of axions, of course this number will be, I mean, if you have more axions, of course the probability to decay is big, right? It grows with the number of axions, but it's still small to detect this spontaneous decay. Then, okay, as in the axion decay into 2 photons, the final states are bosons, in this case photons. One can stimulate this decay if we have the axion in a photon background, and this photon background is centered or has a frequency, or these photons have a frequency equal to the axion mass over 2. So in this case, the axion decay is stimulated. And if you calculate the lifetime of the axion, okay, this is the lifetime for a spontaneous decay. So we have to put this factor in the formula, where F gamma is something like the occupation number of the background photons. Then it's given by this, where this rho is the photon energy density and delta omega is the bandwidth of the photon, in this case of the photon field. Then what happened is that let's put some numbers. How much is this enhancement for the axion decay rate? if we put, for instance, a power electromagnetic wave with 1 kilowatt power and a bandwidth of megahertz, and during 1 second and in a volume of 1 meter cube. So we find that, this F gamma is of the order of 10 to 25. So what happened is that the spontaneous decay of the axion is enhanced by this factor, only because it's in a photon environment. So it's like the photon environment trigger the axion decay, stimulates the axion decay, and okay, it's of course more likely to find this signal from axion decay in this case. So some question so far? Okay, I assume there is no question.
Hola, Ariel. I am
Hola.
Marcelo. Well, the axions cannot decay. So how do you expect to detect those axions? I mean, the only way would be through gravitational effects, or what's the idea of the experiment?
But what you're saying, that the axion does not decay?
Well, since the lifetime is 10 to the 42 years, forget it. Then it doesn't decay. It does not decay at all. So
no, but I'm saying that we can stimulate the decay, putting a photon background, and the decay rate is enhanced by 25 order of magnitudes if we put these numbers here.
And which is the mechanism responsible for those enhancement?
The Bose enhancement.
Yeah, how
it's because of Bose. It's because of Bose statistics. If you have an initial condition with a let's say a occupation number of photons, the decay rate is
oh yeah, I understand. Yeah, okay. Yeah, okay.
So now the idea is the following. The experimental idea is the following. So we assume that our environment is filled by dark matter, okay, and we will assume that the dark matter is composed by axions. Okay, in all these calculations, we assume that the axion is all the dark matter. So we expect to have dark matter, a local energy density of dark matter, of axion dark matter. So we are going to stimulate the decay of the dark matter here in the lab location. So the idea is to send out a beam of electromagnetic radiation. Let's say this photon gamma naught, this one. And okay, it's not just a photon, it's a wave with a huge photon occupation number. So we expect to enhance the decay of the axion. And on the other hand, okay, first the decay will be enhanced, right? So we expect the axion to decay. And now, if we assume that the axion is at rest, let's say we working in the axion frame. So as we stimulate over, let's say, this line, right? Over the line on the of the beam, in this case of the incident photons. So because of this stimulation, one photon from the decay adds to the initial photon, right? And there is another photon which from the decay as well that has to be ejected, right, in the opposite direction, just because of momentum conservation. So this photon, this this backscattering, let's say this backscattering is what we call the echo, and is what we are planning to detect. So, okay, we can calculate what's the power of this backscattering given by this formula, where T is the time which the outgoing beam, and in this case, the photon beam, the initial photon beam is turning on. And the P naught, the nu, is the spectral power of the incoming wave. And rho is the axion dark matter energy density. And G, the coupling to photon. So this is the total power in the echo wave, right? The wave we want to detect. So let's again put some numbers. For instance, for a power of 1 kilowatts, which is easily, you can find this power in a microwave, oven, and during a time of 1,000 seconds. And if this wave, I mean the incoming wave, has a bandwidth of 100 hertz, okay, let's say some very realistic and easy to find parameters, one can find that for a typical QCD axion, dark matter, the echo power is of the order of 10 to minus 22 watts, which is a very good number. So far, it's a very good number because it's easy to detect this power with current radio astronomy equipment. So yeah, so far everything is nice, but okay, there is a limitation of this. Okay, we can, unfortunately, we cannot detect the axion so easily using this method, because what I will say now. Okay, so we got the paper about this, and what happened is the following. Okay, this vector MB is the momentum of the axion, because the previous calculation was made assuming that the axion is at rest, but we know that in the lab frame it's not at rest, right? It moves with some the axion. There is like an axion flow which moves with some velocity, and also it has some velocity dispersion, right? It's not completely cold. It's cold. The velocity dispersion is small, but it's okay. It's not zero, so we have to take into account that. So okay, let's assume that we have an axion with velocity v. So the momentum, because it's non-relativistic, so the momentum is mv. And we have outgoing photon, the stimulator in this case, right? The photon we send out to space, which has a momentum omega naught. So by momentum conservation, by momentum and energy conservation, one find that the momentum of the echo photon, the photon we want to detect, the echo, this omega minus, is ejected in forming an angle phi respect to the initial beam, the outgoing beam, or respect to the incoming photon. So this phi, by energy momentum conservation, is more or less twice. No, it's okay. It's twice plus corrections of order v squared, which is very small. Is twice the transverse velocity of the axion with respect to the incoming photon. No, sorry, the outgoing photon. Yeah. So yeah, that's So what happened is that we can see that because of this transverse effect, the echo is not exactly back at the emission spot. It will spread. Yeah, it will spread especially. So in that case, we are limited because we know that we cannot collect all this power calculated, which is 10 to minus 22 watts. We cannot collect all this power because it is spread over the space. So the only way to collect all this power is to have an infinite detector, right? I mean, a detector with an infinite surface, but it's not possible, of course. So we are limited by the size of the detector. Then we define this d max, which is the maximum distance where if we have, let's say, if we have a detector with let's say a dish, it's a radio telescope, let's say. So if this dish has a radius r, so we can detect echo only coming from a distance given by d max. So echo coming from distance higher, I mean larger distances, will be out of the dish of the detector, so we cannot collect it. And then, okay, on one hand, the echo is spread in space. So the formula is not what I gave first, but is this form. This is the actual formula for the echo. You can see that here we have this r, so it's limited by the size of the detector. And we have this b perp, which is the transfer velocity of the axion respect to the outgoing photon. So we can see that if this b perp is 0, for instance, if they are aligned, right, its results blows up, right? But in that case, we have to consider that it will be limited by how long the outgoing beam is turning on. Because of course, once we turn off the beam, there will be no, I mean, the power of the echo will not grow anymore. So okay, but for realistic considerations, this will be the final formula to calculate. And this C is just a form factor which depends on the configuration of the detection configuration. Let's say how we are putting how we are setting up. We set up the experiment, where we put the dishes and stuff. So okay, the echo is also spread in frequency, and the frequency of the signal, I mean the bandwidth of the signal, is more or less the minimum between the momentum dispersion of the transferred component of the axion flow and the bandwidth of the beam. So some questions so far? Okay. Okay. Now one can think about the effects from the shape of the outgoing beam, because for instance, if you see this picture, this is like a typical shape of a beam sent by let's say by a radar. So we feed a dish, and this dish sent an outgoing beam of electromagnetic radiation, and this electromagnetic radiation has this form. Yeah, one can think what happened if this shape affect the echo signal. And okay, we calculated using a shape of using this shape. We calculated the echo, and we found that it does not depend on this geometry. So this is the paper, and yeah, we found that it does not depend on this. So yeah, it's not a problem. Yeah. Now, as I said, that the echo signal will depend on the velocity of the axion in the lab frame. So it will depend on the model of the dark matter phase space distribution, right? So we calculate the echo signal assuming two different models for the local dark matter density and phase space distribution. So one of these model is the cluster ring model, which is was proposed by Pierre Sikivi. And in this model, I am not a real expert, but I just managed some basic features about it. So but the important thing is that in this model we have as a local dark matter, we have a big flow, okay, moving in some direction, and this flow is very cold. For instance, let's say that the velocity of this flow is 300 kilometers per second, but the velocity dispersion is of the order of 70 meters per second. Okay, this is just a bound. It's actually less than 70 meters per second. So it's a very cold flow. And the energy density is of the order of 1 giga-electron-volt per centimeter cube. So in this model, here there are some papers of it, and some claims that this model has been observed. You can see they are interesting. So in this model, it's supposed that the direction of the flow is known, but with a very small uncertainty. And this uncertainty makes a transfer velocity of the order of 5 kilometers per second. So this will be the uncertainty in the direction if we translate it to transfer velocity, right? Because if there is an uncertainty in the direction, so there will be a transfer uncertainty in the transfer velocity, which will not be exactly zero because we have this direction uncertainty. So this is like 5 kilometers per second. So we use this number to compute the echo signal. Then here there are some simulations of the echo signal for this cluster ring model. This is the intensity map as a function of time. Every picture is a different time. You can see this MT, which is just a dimensionless parameter, but that involves the time. So we can see that as the time goes on, right? We can see that this red region will correspond to the echo intensity. We can see that it spreads spatially to the right. So this is the effect I was talking about, that the echo is spread in the direction of the transfer velocity of the axion. So we have like this such shape. So yeah, so we can see that if the detector is limited, right, we will detect only a part of the echo, not all. So we will need a really big detector to collect all the power. So yeah, at this point, in this part of the picture, the echo is sorry, the outgoing beam is still on, but here it's off. So one can see that this sausage just moves rigidly to the right, right? It leaves it. So yeah, now we also compute this intensity map for the isothermal model, which is like the standard model of the energy density distribution and phase space. So in the isothermal model, the velocity of the axion flow will be more or less the velocity of the sun in the galactic frame, which is 20 kilometers per second. And in this model, the velocity dispersion is of the same order of magnitude as the velocity of the flow. So it's not like the Castor model where the dispersion was very small. So in this case, what happened is that the echo does not have a preference direction to spread. It actually spread in every direction because of this energy dispersion. So here we have the intensity map of it, the same as before, but for this isothermal model. So you can see that it doesn't, it is spread actually in all directions. You cannot see the spreading because it decay, right? I mean, the intensity at large distances will decay as 1 over the distance square, right? So we cannot notice this, but it spreads actually. So when we turn off the beam, so the echo just disappear. So you can see here for different times what happened. Okay, now let's talk about the sensitivity of the idea. So this is interesting because in the window where the axion can be the dark matter, for the echo method, we expect to have a signal which is in the range of microwave or radio waves. So in this range is where the sky is mostly transparent. Not mostly, it's really transparent. So there is no absorption of something in the atmosphere. Then, yeah, we are lucky because of that. So in this range, we know that is in the range where most of the radio telescope work, and they're very sensitive. They can. The CMB was first detected by a radio telescope, and it's very small, very feeble signal, right? But it can be detected because as I said, the sky is transparent. Yeah, so we are just in the good range to do a terrestrial experiment. Then we calculated what's the sensitivity we expect. Okay, so we assume to make this plot, we assume that the receiving dish, I mean the detector, has a radius of 100 meters. So now today the biggest radio telescopes, in which I think is in China, has a radius of 250 meters. So yeah, we could also use that number, right? But okay, we will have a better sensitivity, but let's just assume 100 meters and a noise temperature. I mean, this will be the total noise temperature, which has to do with backgrounds. For instance, the CMB is a background that can spoil the signal, right? And of course, instrumental noise. But this 20 Kelvin is like a typical number. It's not. It is realistic, 20 Kelvin. So we are using this number. And yeah, so we can see the parameter space that we can, the axion parameter space that we can prove the axion. And this the solid blue line corresponds to the sensitivity. The solid blue lines in this picture and in this one, the left one corresponds to the clustering model, and the right one to the isothermal sphere model. So the solid blue line, it's the sensitivity, assuming that we spend 100 megawatt year in energy, because we need energy. We need to turn on the outgoing photon, right? The outgoing beam. So this if we spend 100 megawatt year to cover an octave in the axion mass range. So let's say from 1 gigahertz to 2 gigahertz. Okay, so we cover, or for 1 microelectron volt to 2 microelectron volts, we cover this axion mass range, and we spend 100 megawatt year in energy. So, but these solid blue lines, they don't say anything about how this energy is consumed. So this is only the energy. If we are more realistic and we say, okay, let's consume this energy by turning on a power source of 10 megawatts during 1 year, right? So we have the same number. We have oh no, this is yeah, this is a mistake. These plots were made assuming 10 megawatts year, not 100, sorry, 10 megawatt. Okay, but anyway, if we turn on a beam of 10 megawatts during 1 year, so we are able to we have the sensitivity showed by the dashed blue lines, okay, which is worse than the other. But we expect that you have a good strategy to try to reach this solid blue line, but it is still not clear how to do it. But in energetic terms, we have this this sensitivity, but we don't know how to do it in a real experiment. So yeah, so you can see that even with the dashed blue lines, this experiment will be good to search for axions or axion-like particles. Especially in the clustering ring model, we have a good opportunity to prove a QCD axion. This DFSC and KSBC lines corresponds to the QCD axion models. Okay, what's next? One thing that it's maybe an issue for this method is that, as I said, the sky is transparent, but it's not 100% transparent. So there are something that can interact with the outgoing beam. So it can we can have a backscattering coming from the interaction between the beam and the atmosphere particles, right? So yeah, if we detect a signal, we don't know if this signal comes from the axions or comes from the backscattering because of the interaction in the atmosphere. So okay, first I calculated the Rayleigh scattering in the scattering of radiation in the atmosphere molecules, and I got that the noise temperature is on the order of 10 to minus 2 Kelvin. So I showed that the previous plot with a noise temperature of 10 Kelvin. So this is below the noise we already have. So it doesn't affect the experiment. But this is just Rayleigh scattering. It's not clear if there are another kind of backscattering in the atmosphere, in the ionospheres as well. So it's not clear, but we found that if the bandwidth of the outgoing beam is much smaller than the axion momentum over 2, right here we have this. So if we make the experiment in this regime, which is realistic, we found that the echo is shifted respect to in frequency is shifted respect to the outgoing beam. You can see this picture here. So this will be the power spectrum. It is normalized, okay, but it will be the power spectrum of the echo, and this is the power spectrum of the outgoing beam. So they are totally separated if this relation is fulfilled. So we expect that any backscattering coming from the atmosphere will have a spectrum similar to this, right? Because the only way to redshift or to blue shift a signal is that in this case the target, let's say the molecules or whatever, the target should have some velocity, right, respect to the lab frame. So if the target moves respect to the lab, so we will have a redshift or blue shift, right, respect to the outgoing beam because of this motion. It's just Doppler. It's just Doppler shift. But for the axion, this Doppler shift is much bigger because the axion moves a much bigger velocity than any molecule or any matter in the atmosphere. So the Doppler shift in the axion echo is much bigger than any other. So we expect to have a total separation between this backscattering coming from the atmosphere and the echo, so we can detect it, or at least the noises will not be a problem. So another possibility now is instead because it will be expensive to construct a very high power emitter, but okay, 10 megawatt we already have for instance the klystrons used to accelerate particles in particle collision experiments. They provide easily 10 megawatts of power, but it's still expensive. So one possibility is to use a natural source. For instance, the sun. We are thinking about the sun, but it's work in progress. So this is just a plot of what will be the parameter space we can we can prove for axion searches. Okay, this is just preliminary results, but this parameter space can be proved assuming that the power of the echo is bigger than 10 to minus 22 watts, which is something detectable. But for the sun, you can see that the axion masses that can be proved are in this range between 10 to minus 2 and less than 100 electron volts. So the dark matter axion are not very motivated in this range, but okay, it's still open, right? And okay, so I leave the conclusions that we think that it's interesting because it needs not new technology. One can do the experiment using a radar, for instance. The radar works like that. They send a beam to a plane, right? So they catch the echo of coming from the plane, right? So it's similar. So it's also applicable in a wide axion mass range. Sorry, from, okay, I put here these numbers, but okay, it can be extended to bigger and lower frequency, but this is usually where the sky is transparent. So one expect to do a good experiment in this range. Yeah, for this is, I think, all I have to say about it. Thanks.
Thanks, Ariel, for the very nice presentation. Very interesting. Does anyone have any question? Cristobal wants to, or no, it's just clapping. Ariel, just a question on the plot that you show, kind of this signal and background peaks. Was like two slides ago.
Yeah, sorry, but I lost the window.
The window. No problem.
Yeah, I don't know where it is. Okay, let's see.
Well, my question goes because they are pretty symmetric. I mean, they are exactly, the peak on both signals are exactly on the same number as far as I looked. Do you have any explanation for that? Is this something very obvious?
Yeah, okay. Let me
yeah, don't
let
worry,
me find the window, and because I don't know what. Oh shit. How to? I don't understand why I cannot find the.
Maybe if you stop share, then you can find the slides and then share again.
Okay, I will do that. Okay. Okay, so now where? Sorry.
The plot where you show kind of a signal of an axion and then a background from these interactions with other. One more. That one.
This one?
Yes, that one. Is that right? Yeah. I mean, the color peaks are kind of your signal, and then you were trying to understand if this backscattering would bother you on the signal, but it shows that it's not. But what came to my attention is that the peaks are actually very symmetric. I mean, they're almost at the same number, let's say, symmetric from 0.
Yeah. It's
is there
because,
any explanation? Yeah, okay.
Yeah, the explanation is because of this, because the what we are plotting in the horizontal axis, we are plotting this omega minus m/2 delta omega. So we made it symmetric. I mean,
it's a difference. Okay, yeah. No, I see.
Yeah.
Okay.
Yeah, it's just a difference. So we just center the plot.
Okay. So this would be kind of an observable to watch if you want to check like signal versus background or something like that, right?
Yeah. Yes.
Okay.
Yeah,
Thank you. Does anyone else have any question? No, I think not. Okay, great. So thanks, Ariel, again for your talk this Thursday. And also thanks to all that came to the talk, and hope to see you next Thursday then. Bye,
Okay.
Ariel.
Thanks. Bye.
Bye-bye.
See ya.
Thank you. Bye to all.
Bye-bye. Thanks.